telescope to understand why and how stars blow up. In addition to his research, he's also developed a series of astronomy coins in conjunction with the Australian Mint. He consults on science fiction movies, he's advised on astronomy-themed art projects, and he's currently working on a book right now, a science-related book. Tonight's topic, Exploding Stars, Dark Energy, and the End of the Universe. Most giant stars end their lives in a brilliant explosion known as a supernova. The massive bursts briefly outshine all the light in their parent galaxy. The past 15 years have been a boom in research for supernova explosions, and they are important for the understanding of the life of stars, but they can also be used as cosmological probes to study what the universe is made of. And how the universe is accelerating and expanding is also the subject of a 2011 Nobel Prize with a gentleman he has worked with, and I'm sure he'll tell you about it. Tonight he will show how our understanding of these objects has revolutionized and what this means for the universe. So please join me in welcoming Brad Tucker.
Thank you, Lou. Just computer.
You want to do the sound test?
Sure. I have a loud enough voice, so I hope everyone can hear me.
Can you hear in the back?
Yep. I'm the only one on TV who they have to turn down the mic for. Great. So thank you all for coming on this great Wednesday evening. Usually when it's anywhere, it's cloudy and rainy, so it's a bonus. So today I was going to talk about a little bit about what I'm doing, and it's aptly called Exploding Stars, Dark Energy, and the End of the Universe. Two themes you'll get at from this talk are we're doomed, and the universe is awesome, but it's going to doom us. So there will be a brief interlude where you won't actually be seeing what I'm showing you. You'll understand a little bit. Just don't tattle on me when we get to that point. And actually, some of the stuff, as I'll talk about later, which is the stuff you won't be seeing, is purely reliant on the Lick Observatory. And so if we don't actually have it, we won't be able to get the results we're talking about. So, a lot of the talk will focus on exploding stars, and that's because these are the tools to measure dark energy, and dark energy is what's going to end us. Well, the sun will end us too, and other things, but let's just ignore that for now. This will end us on a longer time scale. And exploding stars, called supernovae, are really cool. And it's a dark image. This is a M82, and it's called a cigar galaxy. And this star is actually an exploding star. And for reference, that's a star in our galaxy. So this object, which is 3 million light years away, is nearly as bright as that object, which is 12,000 light years away. And that's because these are very energetic things. They're equal to 100 million, billion, or Google says 100 decillion lightning bolts. So imagine one lightning bolt, and then imagine 100 million, billion of them, all in one. That's what happens when a star blows up. Now you'd say, oh, these are really big explosions. They don't happen that often. Well, the one thing I can conclusively say we do know is these are actually really common occurrences. If you assume, and it's pretty well known, that each galaxy has roughly 100 billion stars. In astronomy, if you're off by 1 billion, it's okay. It's a great job to have. If every galaxy has about 100 billion stars, and we know there's roughly, again, about 175 billion galaxies in the universe, that means that every second, 50 stars blow up. So, already in the time of talking, I've killed thousands of stars. It's kind of a powerful tool to have. They're very common, so to speak. So which means is, if we want to use them to study anything in the universe, we have a good tool that is abundant, and it's out there. Now, the other great thing about it is, this is one of the few fields in astrophysics where the amateur astronomy community has a very big impact. A lot of the nearby important supernovas that we've ever found have been from amateur searches, not our professional searches. And in fact, this one, which we call 2014J, supernova are named by the year and then a letter of which it fell for, so that's the 10th supernova 2014. And then you just get to telephone numbers, AG, blah, blah, blah. This was found by an amateur survey. So how do you say that a star that's 2 to 3 million light years away, relatively nearby, was missed by every professional telescope? That's because we weren't tuned for it. So if the amateur community did not find this one, which will go down as the most important supernova in history at this point, if they didn't find it, we would never know. And so it's actually a really cool community to have where the amateur astronomy community really helps out the professional community. Now, supernovae in their own right are really cool. Why? They allow a lot of different things to do with them. They're one of the few things in space when things take millions, if not billions of years, that actually happen in a few months. They'll blow up, you'll see them blow up, and then they'll fade. They happen on human time scales, and less than that, they happen on monthly time scales. It creates a very dynamic kind of universe. We think of the universe as this stale thing that just goes on, but really it's it's the happening place to be. They influence stellar evolution, how galaxies react. We can use them for studying the universe. We get to see all sorts of cool things like black holes and gamma ray bursts and everything you can think of that's cool. I don't think planets are cool, sorry. No, planets take away my money. No. Anything that's cool really has to go to supernova. Well, I guess a supernova can destroy a planet, so there you go. Now, let's take a step back. What are supernovae? So there's actually lots of different types. And we broadly call them by these various telephone numbers based on how their explosion looks. So if we measure how bright they get in blue, and we monitor how blue they are over time, you can see that they have different shapes. And as I'll say in a second, this is actually an outdated mode of talking about it, but astronomy likes to hold on to our nomenclature, so we stuck with it. And the real reason I like this plot is something this. So this is called 1987A. It was the closest supernova essentially in human history. It happened in the Large Magellanic Cloud, which is one of the neighboring galaxies that you can see with your own eyes in the southern hemisphere. And this is probably the most studied and well understood supernova that we've ever had. We have 10 to 20,000 supernovae now, and this is the most important one so far in terms of our understanding and how much time and resources we put in. And what do you notice? It doesn't fit any of our normal templates and classifications. So the one we know doesn't fit everything else. Now that obviously raises the flag. There's a lot to know. We could just say that's weird, but, well, it's hard to say the thing you know about is wrong. So it shows that there's a lot of stuff we have to do, but there's a lot of cool things that we get to study for it. Now, what do all these telephone numbers mean? Well, Fritz Zwicky, in the 1920s and 30s, started to find supernova, and some had hydrogen and some didn't. So if it didn't have hydrogen, he called it a type 1, because why not? And if it did have hydrogen, it was a type 2. But then he found some of the ones that didn't have hydrogen had silicon, so he called them a 1A, and they didn't. And further, there was helium, and there wasn't helium, and so on and so on and so on. And for tens of years into the 80s and 90s, this roughly held. But then we just started, things weren't quite what they seem. So when we actually look at these categories, when we look at the individual element, what's going on, you can see these blue shades. There's lots of iron in all of them. So supernovae are what produce iron in our universe. And yeah, this type 1A, it does have silicon, it does have sulfur and iron, it doesn't have hydrogen. Okay, fine. Now, this type 1B, it does have helium, this type 1C doesn't, sure. But then we started to find they actually did have hydrogen. And then we have type 2s which have hydrogen, but then we found that the hydrogen didn't go away. So the only thing we realized is that something was exploding. We really didn't know anything much else than that. So it's a really outdated mode that we still stick with. But eventually it's led to us to our understanding that every group of supernova, the 1Bs, 1Cs, the type 2s, all of the ones that we think are different, are actually physically related, where these ones are the ones that are kind of weird. Now, there is something we do know, and that is how to find them, which is good, right? What you do is you observe, you look at a patch of the sky, and a few days later you go back, and you subtract the two, and sure enough, there was a supernova that went off in that galaxy. It's something that we can do a lot of. So what you do is you say, okay, well, here's an image. 4 days later, we went back and took this image. Can anyone see where the supernova is? So there will be something in this image that is not in this image. Now you'll say, okay, well, those three look different, and those two look different. that's not because, if anything, that's only due to the moon. So the moon got a little bit brighter, the weather was a little bit worse. So you have to take into those accounts. There's other things. So there's this spot here, there's that spot there and there. Those aren't real, those are cosmic rays. They're the, it's the junk of the universe, these high energy particles bombarding us. So you have to take all that into account. There is something new in this image that wasn't in this image. Who can find it?
Well, there's a dot in the lower right, up above there.
Nope, that's a cosmic ray.
Lower left.
Where?
Lower middle.
Cosmic ray.
Bottom left.
Bottom left? Here?
No, bottom.
There?
Nobody says there's something about
No. Any other, you got an idea?
Oh, yeah.
Confidence. Confidence is the key. And if it's not right, you pretend it's right.
Where's the There's an extra dot.
Aha! Good eye. Well done. That is the supernova. Can you guys see that?
Yep.
Well, there's actually a second thing that's changed. So, luckily, we don't sift through millions of images. We have computers to do this now. So if you subtract the two, there's actually two things that have changed. There's, as you aptly pointed, that little dot, which wasn't there before. But mathematically, when you subtract these two, that in the middle is brighter than that one. And that's because there was a supermassive black hole that just ate a few stars. Now, that's great, but I don't care. You know, they're cool for their own right, but for what I want to do, I don't want to find them. So you have to, even when you find these, you have to go and follow up. Is it a real object? Is that what you're trying to do? So we know how to find them. We're pretty good at it. What else do we do now? We know that they're bright and they're long-lasting. So this is the movie, and this is what we call Supernova 12FR. So 2012 FR, so it was FR alphabetical if you want to go through all those combinations in 2012. And it exploded in October, late October, and the movie ends in January. So that. Those are all stars in our Milky Way. The galaxy is 13.6 million light years away. So when you play this movie right here, no, that's another one. That's 11 FE.
Is it
I'll telephone them.
1365?
Huh?
Is it 1365?
This is NGC 1365, yes. That's right. So when you play this movie, out of nowhere, that blows up. So that, again, which is 12.5 million light years away, is brighter than these stars thousands of light years away. They're very bright, and it lasts a long time. So we know that. All right. Now, we do know some physical things about this. So I'll first talk about what we're calling the core collapse supernova. So those are those things that I call type 2s and 1Bs and 1Cs. And luckily, stellar evolution is something that actually works with us. So our understanding and belief of how stars evolve has told us that when you have a star and it's burning through its hydrogen and its helium, so our sun is currently burning hydrogen, and when it goes through that, it'll start burning helium. Well, if a star blows up at the point where it's still burning hydrogen, when you look at it, you'll see hydrogen and you'll see some helium. Great, we do see that. And if you evolve it a little bit long, you use up all its hydrogen and you start burning helium, what do you see? You see a star that's dominated by helium, but no hydrogen, a 1BC, or 1B. You evolve it a little bit more, and you get rid of that helium, and you start burning carbon and oxygen and nitrogen. You don't have hydrogen or helium. That's great, because we think we know that, and that's something we see. So naturally, we have to put them together. And when we look at the insides of stars, we do see that on the outside you get hydrogen, then you get helium and carbon and oxygen and so on. And when you get down to it, you get silicon. So then you would say, okay, the ones that had silicon but no hydrogen or helium or carbon must have burned all the way through and exploded at this stage. Okay, great. That starts to paint a picture. But how do these actually blow up? Now that's really where the cool thing happens. So as the star evolves, it starts to puff out its layers. So when our sun burns through its hydrogen, in order to puff out that, in order to keep it balanced, it starts to push that spent fuel away. So this is what we call a red giant star. So as our sun uses up its fuel, it will start to slowly expand. So the red giant, what is the sun, will grow and grow and grow, so it'll destroy Mercury and Venus and Earth. Mars may or may not survive, so if you want to buy land on some planet, go ahead and buy Mars. Yet it won't be hospitable for about 10 billion years, but sure, why not? The moon's not a good place to invest. As you puff out those layers, well, you still have this mass, it's just kind of like spent fuel, and you still have gravity pulling you in. So what has to happen? Well, the star has to burn more fuel in order to counteract the pressure of gravity, and then more and more and more. So you get this epic battle between pressure and gravity. And at some point, the star cannot sustain itself, and gravity pulls everything together and ignites the inside of the star, and then it blows up. So it's something we literally call a core collapse. The core, the inside of the star, collapses, everything comes crashing down, and it ignites in a big stellar bomb. So it's a really cool thing, and we wanted to put this to the test, and we were like, well, what's the best way to do it? Well, luckily, again, we had this supernova called 1987A. It went off, as I said, in the Large Magellanic Cloud, so one of these neighboring galaxies that we have, just very nearby. And the good thing about this galaxy is that we were able, beforehand, because people were studying the individual stars in this galaxy, to resolve the individual stars before the supernova. So in early January 1987, when someone realized there was something that just blew up, which is here, it was really bright. What we were able to do then is go back to the images that were taken before the explosion and see, was there a star located at the center? And sure enough, the object pointed to with an arrow is exactly at the center where that supernova took place. Now, supernovae do fade and they do eventually go away. So if you wait long enough, hopefully this light should fade. All the energy and explosion from the supernova should go away. And that star should disappear if it was the one that blew up in the way we thought it blew up. And sure enough, that star does not exist anymore. We've been able to image before the stars, see them blow up, and then confirm they disappeared. And what we found now is we're able to know that that is a 14 solar mass, so a star 14 times the mass of our sun, and something called a blue supergiant. So it's a large star in a certain evolutionary process. And the interesting thing about it was the first one we were able to do this technique with, this weirdo, if you remember from the earlier plots, that star was never theoretically predicted to blow up. All of our models said, oh, you can never blow up this type of star. It's impossible. That doesn't make sense. Sure enough, the first one we figured out was this.
What's the distance to that again? I forget.
The Large Magellanic Cloud?
Yeah. Roughly.
I think it's about 500,000 light years.
Oh.
Yeah, it's pretty nearby relatively, and so to speak. Again, 500,000 light years is close. Now,
how come they didn't think it would blow up? I mean, 14 is well in excess of 3.
it is, but it's a stage of evolution. So when you're what you call a blue supergiant, you're still actually a relatively young star. So when we look up in the night sky, blue stars are usually younger than red stars, and that's because the hotter you burn something, the color changes. So if you're hotter, that means you're still burning less fuel, and therefore you're younger. So we never thought a fairly young star could blow up. And this helped paint the picture that really changed that it doesn't matter where you are in your life, the bigger they are, the more you blow up. So it's kind of like celebrities almost. You know, it doesn't matter how long they are, where they are in their career, the bigger they are, the more likely they are to fall. Yeah?
160,000 light years.
There you go, even closer than I thought. Relatively close. See, Google. If you need to know something, and it can be looked up, you don't need to know it. Right? Hey, that's what physics is about. It's about applying things. And so that's right. It's one of the closest galaxies we have. But with the advent of the Hubble Space Telescope and our large telescopes like the 10-meter Kepler telescopes and the 8-meter Gemini telescopes, we've been able to do this on a lot more supernova now. So this is something called a 2008 CN. Again, this telephone number. And it's a stock standard type 2, so one of these that we had just thought didn't have any hydrogen. And there's a supernova when it went off. And we went back. So on the top, we have before the supernova. And on the bottom, we have after the supernova. And sure enough, there's a star right at the center of the explosion, which has just been confirmed now that it's disappeared. A couple other different types, this thing, 09HD, another type of supernova. Again, there's a star right at the explosion of the supernova. And there's this one, a very nearby one, 2011 DH. It was caught very early. You can see here, there's nothing there, and there's something there. Again, we've had HST for this. Now, this one's a little bit slightly different, but it's the same argument. So here is the image before the supernova, and this is the image with the supernova. Okay? So here we have a fairly bright star, and here we've had, so this is 2013, so it's about a year and a half after the explosion happened. The light from the explosion is fainter than that star. So if that star didn't blow up, you wouldn't be able to see the supernova anymore because it'd be brighter than the old supernova explosion. So it's another way, even more creative way, of saying that star blew up. Because if it was there, we should see it there, but we can't. And if you actually add up all of this picture, this slide says as of now, but it's as of 2 years ago, and we've added about 10 more of these. You can see, so this is in terms of size of the sun. So this is 5 times the mass of the sun. This is 30 times the mass of our sun. You can see the range of supernova we get. Before we were able to do this technique, we always thought that supernova would explode between 5 and 10 times the mass of our sun, the lower limit. And of course, we're finding it's about 7 to 8. So perfectly within our prediction. So we can't do something, right? And we can paint a picture now of how stars evolve and what they look like when they blow up, related to our telephone numbers. So our 2P is a red supergiant, our weirdos, just 87A is a blue supergiant, yellow supergiant, and there's a whole bunch of things. But then there's a category of things we know explode, but we haven't seen yet. So I said that this is pretty much most of the supernovae we know about, minus this other type that I get to. But of course, knowing, as soon as you think you know something, you realize you don't know it. Again, science is one of the few jobs where you're paid to make sure you're wrong. That there's a whole new class of supernova. So here's the plot I showed before. So this is brightness. So those are all the ones I talked about right here. That's how they fall in terms of brightness and how they long. This is the weirdo class that I was going to talk about. But then there's this new class. 10,000 times brighter than our brightest supernova we had. It came out of nowhere 5 years ago, and now we have 40 of them. And the great thing about this is we relatively think we know what these are. And these are the first generation of stars. So stars, just like families, are in generations. You had your first generation of stars that died, that gave birth to a second generation, that died and gave birth to a third generation. And the earlier generations were bigger than the later generations. That's because in the early universe you had mostly hydrogen and a little bit of helium. Well, it's easy to stick lots of hydrogen together, and so these stars are between 100 and 1,000 times the mass of our sun.
This is what they're calling the hypernova?
It was long believed this was a hypernova, but yeah, that's right. It's now superluminous supernova. But there was also a mixture related to gamma ray bursts on that too. So these are the first stars blowing up. So most of these live to only be about a couple million years old, relatively to most of these stars are between 5 and 10 billion years old. These happened between 200 and 500 million years ago, after the Big Bang, whereas these are 6 to 7 billion years after the Big Bang. These are really the first stars blowing up. And we've even predicted, based on models, that you can get a star that is 55,000 times the mass of our sun blowing up, which would put it about here. Or maybe even there. And telescopes like the James Webb Telescope, that apparently you guys are getting to talk about soon, are hopefully, that telescope will be among the first to find these. Now, if these are really what these are. So, now let's get to the cool ones, so to speak. And these are what I call the weirdos. And these are the ones that we use for cosmology. So So, of course, it's very concerning when I say the weirdos are the ones we use for understanding the universe. And that's because it's something called a thermonuclear supernova. So the rest have been core collapse supernova, when the inside of the star collapses due to gravity and blows up. These, on the other hand, are very different. We know, and by know I mean at least 50% sure, so we know it, that it involves a white dwarf. And a white dwarf is an object which has gone through the evolutionary processes, so our sun will become a white dwarf in billions and billions of years. And it gets a neighbor next to it. Now, what the neighbor is really the seat of controversy. It's long been believed that you get something called a red giant. So let's take our solar system, for example, because there's a long-held belief that Jupiter is kind of a failed star. So let's say we get a star the size of Jupiter. Jupiter turned into a star. Well, it would evolve a lot slower than the sun because it's smaller, doesn't need to burn as much fuel, just like cars. So our sun would have turned into a white dwarf, and then later on, Jupiter would have turned into a red giant because that stage happens after a white dwarf. Well, if you get things that are close enough, the white dwarf still is pretty heavy and has lots of gravity. It can actually suck, kind of like a zombie almost, like sucking brains out or something, the outer edges of the star. So if you imagine our star, our sun, has hydrogen on the outside, well, if you had another heavy object next to it, it'd be pulling all of that hydrogen right off of it in this big stream of hydrogen. Well, Chandrasekhar in the 1920s said that once you get a white dwarf that reaches a critical mass of 1.4 times the mass of our sun, it automatically blows up because it's not a sustainable system. Well, we said, we know these systems exist. We know there's white dwarfs with red giants. We know this process happens. Well, if these are all happening, that means they're all blowing up at the same amount of mass. They're all blowing up at the same luminosity, the same energy, the same brightness. And therefore, these might be the standard candles I'll talk about, which is putting the picture together. But then someone said, all right, let's just have a backup plan in case that's not right. And that is, you just get a smaller star, so just a normal main sequence star like our sun, and the same process happens. And then there was a wild idea, wild at the time where no one believed, and now of course everyone believed it, because it's probably right, that instead of a normal star like this, or a red giant, you just have two white dwarfs, and they run into each other, and blow up. Now, as I'll talk about in a second, we have no idea what this is. We know how to use these things, which is always great, but we don't know what they are. Not knowing something has never stopped us in astronomy. What we do know about these things is that they all happen in the same process. They're not standard candles, they're standardizable candles. Okay? So, what do I mean by that? A star blows up, and it reaches a certain brightness. Well, naturally, it takes a while to get to that brightness and then fades. But if you have the same type of star, but is a little bit brighter, it takes a little bit longer to get to that top, to that maximum, to its peak brightness, and then a little bit longer to fade. Well, what was discovered in 1993 is there's an inherent relationship to how bright it gets and to how long it takes to get to that brightness and then fade. And if you correct for this trend and relate it to distance, you get this on the right. They all follow the exact same form. So if you can take out this relation between how bright they get and how wide they take, what we call the stretch, and you can relate that to distance, you can get something that has the same brightness all the time, and then therefore use it to do measurements in cosmology. So by doing this, we get something this. Velocity going out from us and brightness. They follow a perfect line. Now, what people did in the 1990s, so my boss, was the universe we thought was slowing down due to gravity. At some point it would stop and then collapse back on itself, called the Big Crunch. So if you have the Big Bang, you have the Big Crunch. Now, what they wanted to do is figure out how slow the universe was growing, when the universe was going to stop growing and collapse back on itself. What they found was the exact opposite. The universe is speeding up. So Big Bang's over here, we're over here now. The universe went like this, it is now speeding up. The universe is growing more today than it did yesterday. It's growing more tomorrow than it did today, and so on and so on and so on. The universe, its growth is speeding up. There must be something causing the universe to speed up, and therefore our universe will have the exact opposite end. It won't collapse back on itself, but will keep going out. Now, this was a radical idea because, well, why would this happen? And multiple groups discovered it, and they won the 2011 Nobel Prize for it, the leaders of it. All of the teams got to go to it except me because I was getting married and I didn't get to go. I got an email message saying sorry. But this is something that was originally started on by Hubble in the 1930s. So Hubble, using a very different thing called Cepheid stars, so pulsating variable stars, so stars that puff out and in, and the more they puff and the longer it takes is also related to distance. So another cool thing, he found that, okay, the further out you are, the faster it is moving away from us. So the universe is expanding. That's something we still call today Hubble's constant. The velocity, it's the speed of the universe. How fast is the universe going right now? But he never realized this because that is his plot retrospect to what we can do now. And that's actually kind of been zoomed in and enhanced because it doesn't really show up. So he never saw the universe was actually accelerating because he didn't have a big enough size to measure with. But now we can see that the universe is actually curving, it's actually growing. It's going like a roller coaster. Now, there's a lot to understand about why this is happening, and I'll touch on this in a bit. But what we need to do is figure out and improve the tools. Because I've said that all of the supernova can be related to this and follow this nice trend, get this nice measurement out. But I've lied. So, this is what a normal supernova should look like, this black line. But we started to notice, and we started to call these after specific types of supernovas. So 1991 T, so T supernova 1991, when you did this, it was really bright. Okay, that's an odd duck. Sure. Then there was another one just a few months later that was too faint. Okay, fine, you have a weird one and you have another weird one. Well, unfortunately, if you were to take 1,000 supernova, 200 are these bright ones, and 300 are these faint ones. So already half are these odd ducks. Okay, well, sure, we just have some odd ducks, but we still have some good ducks. But regardless, we can still kind of do this relation that we talked about. So, okay, that's fine. Then we found another odd duck. So this is the faintness, so brighter supernova, fainter supernova. And this is that peak, so how long it lasts. Well, then we found a really bright one, but didn't take very long to get there. Okay, that's another odd duck. So we're at 3. But then we found one that was very faint, but took a long time to get there. So that doesn't work either. So now we're at 4 odd ducks. And unfortunately, these have 50 and 70 friends. So now we're at lots of odd ducks. And if you actually work it out, we have about 12 different types of these that we use for cosmology. Now, that's not very good, even by astronomy standards. But what we wanted to do is see if we can apply the same techniques to try and figure out what's going on with these stars as we did with these big stars. So this is 2011 FE, so this is the one I think you brought up. It happened in M101, fairly nearby. Really nice nearby galaxy. So the supernova, so if we zoom in on this galaxy, we zoom in even further, that little circle there should be the center of the supernova. So this is before the supernova went off, before the star exploded. If you draw a radius, where anything in that radius could potentially be the star that blows up, you don't see anything. The nearest star, these two, it's a 1 in 80 billion chance that those are the stars that blew up. It's even bad for astronomy standards. We know this technique of looking for the star before it blows up works. So why didn't it work for this one? Okay. Well, firstly, we believe that there's two stars that cause these things to happen. This white dwarf, this very massive, small object that our sun's going to turn into, and something else. Well, unfortunately, we're never going to see the white dwarf. It's too faint, it's too small. But we should be able to see what this other thing is, the thing that's having its stuff stuck off of. So if it's a red giant, it should be brighter than that middle circle. Nothing there. If it's a normal-sized star, a main sequence star like our sun, it should be just a little bit smaller than that circle. Nothing there. The only possibility that's left, it was another white dwarf. Because if you have two white dwarfs running into each other and blow up, you can't see either one of them, and you should never see anything there. Okay, so maybe there's just some white dwarfs that run together and blow up. Okay. Now, naturally you'd say, what's the problem with this? A white dwarf, so something to become a white dwarf takes between 10 and 12 billion years to evolve. So our sun's about, let's say, call it 5 billion years. It has another 5 billion years to go before it starts as a red giant phase. And then a few billion years even more to get to this white dwarf. It takes a very long time. Okay? Our universe is 13.8 billion years. How do you get two stars that take 13 to 14 billion years to both evolve and then blow up? And then how do you get stars that occurred 7 billion years ago that are 13 billion years old to blow up? And the universe is 13.8 billion years. We're missing about 6 billion years somewhere. So the problem is, while a few of these two white dwarfs should blow up as supernova, they cannot, for the life of us, understand how we get so many of them. It's a numbers problem. There can't be that many that are blowing up like this, and how much we're seeing. So let's start looking at a few others. So this is the one in the movie. It's just upside, mirrored. That's the supernova.
That's really pretty.
Using infrared imaging, so looking in redder colors than our eyes can see, with an 8-meter telescope in Chile, we imaged this area beforehand. And we were actually able to go deeper than Hubble, which was the previous image I showed. And we were actually able to conclusively say that it must be two white dwarfs, or two white dwarfs that are smaller than that. Okay, so we have two of these. Well, the odds are that two supernovae at random, just because they're nearby, that can do this, again, doesn't work statistically. It's about a 1 in a million chance. Which, okay, maybe in astronomy that's fine. But it makes us uncomfortable. Okay. Let's see, maybe there's another way we can do this. Let's scrap this technique altogether. In 2008, someone was looking at a galaxy at another supernova, 2007 something. And all of a sudden, so this is an X-ray, so this is the things that we use to image our bones. You can actually look at galaxies and see stars. All of a sudden, just for a few seconds, so this is in seconds, so that's 600 seconds, so 10 minutes, this big bump happens. Okay, well, what happened? There was actually, luckily, a supernova that went off while looking at the other supernova. Now, sometimes you have to be lucky. There's nothing wrong with being lucky. Luck leads to Nobel Prizes. Now, okay, what's this bump? Okay, it's a real supernova. So luckily, they caught onto it early. They were looking at the data in real time, so they triggered all of our normal telescopes to find it. Something interesting happened. This is something we call a shock breakout. So when a star explodes, you can actually see the shock wave before the star explodes. So imagine for a second a nuclear bomb. It's not really the best example, but it works. When a nuclear bomb goes off, you get the shock wave go through, and then you get the nasty bits after. When a star blows up, and you get everything collapsing down, you can actually see the ignite of the core go through the star, and then the star explode. Now, this only lasts for on a scale of minutes to hours, which means you have to be lucky or you have to plan it well. And how you plan to predict where a supernova goes off and observe it a minute after, that's hard to do. And what they found with this supernova is that, so this is the normal light curve. So this is 14 days after it blew up. So the peak should be about here. Less than a day, it's actually as bright as the peak. They were actually able to see the shock wave go through the star and then the star explode by being lucky. Now the cool thing about this, at least with this one, we call 11DH, is one that we had this Hubble imaging of pre. And our models of what the star is, so you can accurately model this type of star that blows up based on how big the shock wave was, matches exactly what we saw from the Hubble Space Telescope pre-imaging and our conclusions. So we have two techniques that give the exact same answer, which never happens in astronomy. So that's cool. We have another technique that we're confident of. So this has only been done for these core collapse, these bigger stars. Let's see about type 1a supernova, these weirdos, these cosmology ones. So we can apply the same thing. We have a star that blows up, so this yellow stuff's a star. Now, if we have another star here, and we have an explosion here, as the explosion comes, it's going to hit this other star. Two things will happen when it hits this other star. You'll get a hole, because the star is blocking some of this energy, but it'll build up in kind of a pressure, and then come zooming around, and shoot the star off. Now, the great thing about this is no matter where you are, you should be able to see it. So, I'm here, I'm on Earth, I have a supernova that blows up, and we have a star that was being sucked from it in front of it. So the shock wave happens, you get a hole, and you can get everything zooming around. What you actually see, if everything goes right, if you're looking down at it, you see this huge peak, and then you get this normal looking explosion here. But even if it's reversed, so the star's here, the donor star, so the one being sucked from is over here, you'll see just a little bit of it. But that's okay. If you have all these different views, if you have hundreds or thousands of supernovas, you'll be able to find these features. So it's using the same exact physics, the same exact understanding as we had from other techniques, which we now have two different ways to verify it, on this. And if you look at it, the great thing about it is this little bump early times, this shock wave, is inherently related to the type of star that it gets hit. So the bigger the star, the bigger the surface area, the bigger the bump. So with the red giant, the bigger stars, you get a really big bump. With stars like the sun, you get a small one, but there's still something there. So, I said at the beginning we had thousands of supernovae, which means we have thousands of supernovae to look at this. If we take all the supernovae we have, so there's about 1,200 in this plot, and we look at it, and we look at different colors, ultraviolet, blue, violet, red, even infrared, there's no bump. So remember, so you can match exactly this plot, should exactly match this plot. So that's 15 days. So 15 days. Where's the bump? So 1,000 supernova don't show this. Now, we have another problem. So, okay, we could say, all right, we can conclusively rule out that any red giant and white dwarf scenario blew up as this type of supernova, which has its reasons. Okay, so there's one, let's be negative Nancy here for a second. When we see a normal supernova, we catch it usually a few days after. So, all right, well, you can see there's a lot less points here than here, and so on. Maybe we just haven't been lucky enough. Maybe we just haven't done it enough. So I've developed another program to do this. So the Kepler Space Telescope, who's heard of Kepler? The planetary finding one, it's done lots of cool things finding planets around other stars. Well, it's kind of in a broken phase. 2 of its things that make it point have recently broken. And we've come up with a new mission. So now, half the time, Kepler will not be looking for planets. It will be looking for exploding stars. And so the project I'm running on Kepler. Now you ask, why would you want a telescope that looks for planets to look for exploding stars? Well, the great thing about Kepler is it stares at the same patch of sky, and even though it's monitoring stars, there's galaxies where those stars are, and it's monitoring it every 30 minutes. Okay? So, these features, obviously, are biggest no matter what on the scale of hours. Okay? Well, with Kepler, we know that if a star blows up, when Kepler is viewing it, we'll see it at least 30 minutes after it exploded. So that one lucky one that we got lucky on the other type, if we're monitoring it with Kepler, we should be able to see 100 of those lucky ones. So we did this. We did this with Kepler. So what you're about to see, you don't see because it's coming in a Nature paper, and if you see it, I can't see it because it's... So let's go back to this now. We can conclusively say that we know about some types of stars, the bigger ones and blowing up, and we can conclusively say it's a mess for understanding the ones we use for cosmology, which is the reverse of the way you want it to be. Now, let's get to the nitty-gritty of how we do our cosmology with. So roughly, all of these points, all of these supernovae follow our nice model of the universe. But if we zoom on them in detail, and this is this bottom plot, what this bottom plot is showing is how well, relatively to our cosmology that we think is defining the universe, is going on. So we roughly attribute our universe to having 70% dark energy, whatever this stuff is that's causing the universe to grow, and 30% matter. And now this 30% matter, 4% of it's the normal stuff that we have, so atoms, protons, and hydrogen. And the other 26% roughly is dark matter, a whole other beast. Just to be clear, dark matter is not related to dark energy. We are just not creative. Now, if we say this is our universe, 70%, 30%, if the supernova match this model of our universe, they should all fall along this 0. You can see they don't. Now, you can say, oh, well, how good actually is that? Okay. So let's take a look about what dark energy is. The way we measure dark energy, what's causing the universe to grow faster and faster, is by just measuring the force of dark energy on a volume of our universe. So we'll take a chunk of universe, figure out how much dark energy is affecting it, we'll call it a pressure, we measure the density of that area of the universe, and then we get something called W. And that's really the strength of dark energy. If dark energy, and it's long been distributed, is this -1, it's something called the cosmological constant. So if you go back, when Einstein created his theory of relativity, he originally developed a theory that said, for the universe, 1 equals 0. Now, in math, we're pretty sure 1 doesn't equal 0. I can't confirm a lot about what we know, but I know 1 does not equal 0. And even Einstein knew this. So he said, there has to be something else to make it 0. So you have to have 1 minus 1. He always thought that there was a -1 that was causing the universe to not grow and contract on itself. But when Hubble, around the same time, discovered the universe was growing and realized it's accelerating, just expanding, Einstein said, well, obviously this doesn't make sense. The universe is more complicated. And he retracted it. He called it his biggest blunder. It was his greatest fault. But when we look at it, when we look at the effects of dark energy, right now our measurements are telling us that it's this -1. What we're saying is that the universe is in a balance between how it's expanding and what's causing it to expand. So, 2 things. Firstly, Einstein's craziest idea, which he felt was wrong, could be right. I mean, that's pretty good. And second, what it means is, if this is true, if this is what dark energy is, it is actually just the energy of space. Now, to make things a little bit more complicated, let's explain how dark energy is affecting the universe. So gravity is pulling stuff down, right? Gravity is pulling us down to the Earth. Technically, Jupiter is actually pulling on us ever so slightly through gravity. So far away and it's so weak, we can't feel it. The Andromeda Galaxy, very, very little, but again, we can't feel it. With gravity, the further something away it is, and the less mass it has, the weaker gravity gets. Okay, we understand that well. Dark energy doesn't play by the same rules. So, dark energy pushes instead of pulling. But let's just say dark energy is pulling for a second. It's pulling you down. If dark energy was pulling, like gravity pulls us down, the effect of Earth pulling on us would be the exact same as the effect of Jupiter pulling on us. Would be the exact same effect as the Andromeda Galaxy pulling on us. Would be the exact same effect as the most distant galaxy in the universe, 13.7 billion years away, pulling on us. Does that make sense? That's good. It doesn't make sense. I mean, there's nothing in the universe that does this. So you either have something in the universe that, as it grows, stays the same, or something that changes with time. Now let's make it a little bit more complicated. I've said that our universe is accelerating. Well, there was actually a period when our universe was slowing down. So the Big Bang happened. The universe was actually slowing down. Big Bang went down. The universe was slowing down, but then at some point, it sped up. Now, if I said dark energy is the same effect no matter what, how does this all come into play? Well, it could be that gravity has the same strength, or gravity's strength decreases with distance. But if when you had a small universe, gravity was still stronger than dark energy. Let's say gravity is 10 in terms of strength, and dark energy is 5. Well, gravity is 10, dark energy is 5, so it's still slowing it down. But the universe is still technically expanding because of the Big Bang. It's slowing down in its expansion, but it's still going outward. So you get gravity 10, dark energy 5, then gravity 9, dark energy 5, gravity 8, 5, gravity 7. At some point, gravity and dark energy had the same effect, and then dark energy kicked in and went boom. So this is why people won the Nobel Prize when you discover this type of stuff. It is a very complicated universe in figuring out what's going on. Now, we can kind of make all sense of this in some ways if we all put all the pieces together. But these are our different models. So when we look at a supernova, if it's down here on this plot, it means the supernova is actually brighter than we thought and therefore closer than we thought. If it's over here, it's fainter and further. Now look at here. This is the same scale as this. So 0.2. So look at that. All of the supernova allow all of these different models of dark energy. For Einstein to be right, dark energy must have this effect of exactly -1. If it's minus 1.000001, it's not the cosmological constant. It's not Einstein's theory. As soon as you get something else, you get a whole different realm of what dark energy could be. When you get something that's more negative, so less, it could be a new type of energy, something we just call quintessence. And that is a new type of energy that for some reason popped into existence and created our universe. If it's a smaller number but really bigger because it's more positive, something called phantom energy. Phantom being, we really have no idea because it doesn't make sense. Again, if we look, all of these supernova essentially allow all of these different models. So we can say conclusively right now that dark energy exists, but our measurements are only good to about 15 to 20%. And we have to get a lot better than that. We have to figure out what's going on. Now there's one more problem with all of this. just as with your odometer on your car, or your speed, or the pulleys, you can figure out exactly how fast you're going at some points, but you can also figure out how fast you're getting there, your acceleration. Basic physics tells us that, and we know it works everywhere. Through the cosmic microwave background, this relic from the Big Bang, this relic energy from the Big Bang, we know that the universe was growing about 68 kilometers per second per million light years. Right at about 300,000 years after the Big Bang. Okay. We've also been able to measure the exact speed nearby. And it tells us it's about 74 kilometers per second per million light years. Now, in order to get from this to this, you have to have acceleration. Great, we know that works in the car, we do it all the time. But if you figure out the rate of acceleration, those don't match up. So if we say our acceleration of the universe that we've calculated from these distant supernovae that I've been talking about, it says that this cannot become that. So what do we have? We have three measurements which don't agree. These two can agree if your acceleration of the universe is different, or one of these can be wrong and your acceleration of the universe is correct. The only thing we're pretty confident of, and by pretty I mean more confident than the others, is that this measurement. So this has just come from the Planck satellite, and it is about a year old, and it's one of the most accurate measurements we've actually had in astronomy. It's a really good success. Now, we have one. Let's look at the other two. So, let's try and improve these other two measurements. Now, this is a supernova in a galaxy. So it's a type 1a supernova. These one we use for cosmology in a galaxy. What do you see here?
Dust.
Dust. Dust is the bane of every astronomer. Dust is, it's just the worst thing. I mean, I don't know. It's worse than the Dodgers. There's just nothing good about dust.
And planets.
Even planets are better than dust. It ruins everything, and it causes problems.
Also causes planets.
Yeah, it ruins everything. Now, but dust isn't the only problem. If we look at all of our errors in doing these calculations, we come up with 124 different errors.
Yeah.
Now, it's not as bad as it sounds. 124 errors, that's not as bad. They vary in strength. So you can pick out which is the biggest number here and which are your biggest contributors. You see here, there's essentially dust. We see how we're doing our measurements, our photometry, and there's some other things. Now, one of the biggest problems, as I said, is dust. Why is dust this problem? We have light from a star or from a galaxy or some object. As it travels through the universe, when it hits dust, dust absorbs blue light. So if you have a star that has blue and red colors, as it passes through dust, the blue will actually be absorbed, it will be blocked by the dust, and you'll just see the red light. When we're doing this with measuring supernova, if we're only seeing part of the light, if we're only seeing the red light, we're going to think it's further away than it is, because we're not seeing the blue young light, and therefore all of our measurements will be wrong from this. We know dust drastically affects it. So if we look at a normal light curve of one of these things, dust can inherently vary the same type of supernova by a lot of light, and therefore by a lot of distance. But we found a way around this. So over here is those same weird units I talked about how well you're doing cosmology, way back here. So our different models of the universe. On here, though, we have the distance the object occurred from the center of the galaxy. Why are we doing this? Dust in a galaxy is concentrated toward the center. Gravity will pull the mass in, so the more inside the galaxy you are, the more dust you get. The further away you get, a lot less dust. And right away, you notice something. The ones that are inside the galaxy have this huge scatter. They allow for these huge different models of dark energy. As soon as you start to get away from the galaxy and kind of on the outside, away from all that pesky dust, you get one exact fit of supernova. Just by simply observing where the supernova are occurring, you can actually eliminate the dust problem and improve your measurements of dark energy and of the universe by 8%. Just simply by taking the same things we're doing over again, but figuring out where they are. It's a very simple thing. Now, why do I need to talk about this? Well, there's another thing. When we're trying to do this, we're trying to make all of these into one, we need to know how bright they are and how long they last. Now, dust will affect how bright they get. So, if we can take into account, and we can take only the supernova that are in these non-dusty environments, then we can solve this problem. But it also relies on us knowing exactly when the supernova got this bright and how long it lasted. Now, if you notice when we do this, let's pick this one. There's 1, 2, 3, 4, 5. There's 6 measurements for a supernova that was lasting 18 days. So it's not very good. Now, what if we had a telescope that could observe these things every 30 minutes? So if you knew 30 minutes when the supernova happened, to 30 minutes how bright it was, and then 30 minutes how long it took to faint. Luckily, we do now. And that's because of this, our Kepler project. By monitoring these supernova, you can figure out exactly to 30 minutes when all of these happen. You can actually calibrate the entire population of supernova using our data from the Kepler Space Telescope and reduce the error and reduce our measurement on these supernova by another 7%. I said earlier, we don't understand what dark energy is by about 15 to 18%. By simply taking these two things, we can improve our measurements of what dark energy is into the order of 1 to 2%. Just by using Kepler and where the supernova are going from. So that solves way back here this part. But we can also solve this part. Parallax. Parallax is a really cool thing. There's very few techniques in astronomy that we're really confident about, and this is one of them. Parallax. Take your finger here, and you just blink your eyes. Your finger is going to move in position with respect to the background. If you're looking at a star, and let's say we look at it in January, and over here we look at it in July, the star will appear differently with respect to the background stars. Now, using simple trigonometry, we know the distance from the Earth to the Sun pretty well. We can figure out exactly the distance of that star. It's a technique that's been around for tons of years, and it's something we've perfected. Well, we can do this, but we can do this even better. So, this is an image from the Hubble Space Telescope. Now, what we did was, instead of just taking a nice, pretty image, we left the camera open and moved Hubble. And that's what you get. Now, normally that looks like a terrible astronomy image. And usually you're correct. But why did we do this? So parallax works when you have two different reference frames where you know the separation between the two. So usually we have to do it by sides of the sun because we really know the diameter of the Earth, or the radius from the Earth to the sun. But what if you actually could use the telescope itself to do parallax? Luckily, Hubble Space Telescope has the shakes. It's a Friday afternoon for the Hubble Space Telescope every day. So when you actually drag these stars, they're actually wobbling. Hubble Space Telescope is ever so slightly wobbling all the time. Now, it's wobbling, so all of these stars are wobbling at the same time. You can figure it out down here. What that means is you can actually use the telescope shakes here to do the parallax itself. So instead of using a distance of hundreds of thousands of kilometers, you can use a distance of about 2 centimeters. Now, if you have a much smaller distance here, you can get to much higher accuracy here. And that's exactly what we've done. We figured out the parallax to a whole bunch of these stars, and this should mean nothing other than the one thing I want to tell you is these measurements are 3 million times better than anything we've done. And that's only because by using the shapes of the Hubble Space Telescope. So we put...
Are you saying that whatever's making the telescope shake, I guess which is a matter of an inch or something smaller.
That's right.
That's enough of a baseline for you? Well, that's pretty remarkable. How in the heck are you doing that? Because always people wanted bigger baselines to try to do parallax.
It is, but if you shrink everything down and you know what your whole system is, you can do it. So luckily, with Hubble, you're orbiting around the Earth at a certain field. So you can use the diameter of the Earth and the shapes of the telescope as your 2 points to do this. So instead of
the shape of
the shape of the telescope and the diameter of Earth. So instead of having a telescope on the Earth and needing it to be on the other side of the sun to do this, you can do the diameter of the Earth and the shapes of Hubble to do it.
Well, why, if you could do it, why do you need both? Why can't you just as Hubble goes around the Earth, that's enough of a baseline?
It is, but we can do better than that. The shapes allow us to do better than just the diameter of the Earth. So the previous measurements have been done with the diameter of Earth, but the shapes allow us to take it one step better.
And are you measuring the distance to stars in our galaxy?
That's right, stars in our galaxy. And the key thing here is we measure the distance to the stars in our galaxy, and then we actually measure them to neighboring galaxies.
With parallax.
Yep. And luckily, we've now had supernovae that have gone off in those same galaxies, so we know the distance to that galaxy. We now have cosmological supernovas. So that first supernova I showed, that 14J, the one the amateurs discovered, we've just measured the parallax to that individual galaxy. We have one of our cosmology supernova. We can actually check the distances by 2 different techniques that we trust and cross-calibrate. So we're now in the birth where all our techniques, we can actually do a checks and measures, where before they've just been kind of running wild.
Well, you're saying that by the parallax method, you are measuring the distance to galaxies?
Yep. Yeah. That's exactly what I'm saying.
What?
That's exactly what I'm saying.
Sorry, Lou.
Yeah.
Well, how many arc seconds of parallax are you getting from this?
Yeah, micro arc seconds.
That's 26 micro arc seconds.
And how are you measuring it? What do you use? A measuring engine, or what do you do? How do you measure such a small thing?
The shapes of the telescope.
Yeah, I know, but how do you measure it on once it shows up on the picture? How do you measure the difference, the picture, the different position of the star?
What's the angular dimension of a pixel?
This is the Hubble Space Telescope.
That's the reason why they drag the telescope.
That's right. So you're dragging the telescope here. You're using the shapes relative to any background star and the other shapes. So you can only do this with Hubble because only Hubble has these very fine pixels. So this is what we call something called the fine guidance sensor. So it's the uber top of Hubble. So it's designed for precise images from Hubble. It's the new camera on Hubble. But instead of opening it, we just dragged it. So what you're doing.
What do you mean by drag the telescope?
So instead of having one image here's the sun right there. We can measure it around here or here. But normally we can only take an image here in January, then an image here in July, right?
Yeah.
But if we're dragging it and we're using the shakes, instead of having only 2 baselines, it's essentially like taking hundreds of different images all at the same time by dragging it. So instead of only one image of a star, you have image.
Yeah, but what do you mean by dragging the telescope?
It's like
We leave the camera open and you move it.
And you move the telescope.
You just leave the camera open and you let the telescope orbit the Earth.
And you turn the telescope in the angle of the telescope.
Yes. We can talk more about it if you don't trust me.
That's right.
Yeah. Hubble trust me.
I'm also very puzzled by this. I mean, if the baseline of your parallax is 2 inches, I mean, or 1 inch, if something is like 16 million light years away, I mean, how can that, I mean, that must be so small. It must be, I much smaller than even the size of the...
So I mean, we can't do parallax to every galaxy in the universe. We're only doing it to a few. We're doing it to stars in our galaxy, which are very close by, and to the closest galaxies that have type 1a supernova with it. You're right, we cannot apply this parallax to the distant galaxies. It just doesn't work.
Will it work for Andromeda?
No, it's too far.
So you got galaxies closer than...
Yeah, these are closer than about Andromeda. They're around Andromeda.
Little dwarf galaxies
Exactly.
or something like that?
That's right.
I'm amazed it even works for that.
So, our shaky telescope allows us to do all this.
Sounds like a Nobel Prize to me.
Really? Pretty amazing.
Probably not, because it'll be right, and you don't get a Nobel Prize if you're right. What does this all mean, though? We found techniques using existing stuff and just being creative about it to improve our measurements of all these different steps. We're finally being able to figure out what these stars are doing. Kind of. We're being able to at least check our measurements different ways. And we're finally being able to improve our measurements so we can understand what dark energy is. Now, if we can understand what dark energy is, we'll understand what happens to the universe. So as I said, the universe, we believe, is going to happen with a big crunch. That the universe is slowing down, it was going to stop and collapse back on itself. The discovery of dark energy led to two possibilities, though. And none of them involved the big crunch. Either the universe keeps expanding, expanding, and expanding, and you get something called the big freeze. Now, this is the more sad, kind of sad, depressing one, so I don't like it. If your universe grows and grows and grows, well, at some point, galaxies become isolated. They're so far apart, you can't form new galaxies. And then stars become isolated. So you look up in the sky, there's no stars. And then planets, and then atoms, and then protons, and then subatomic particles. Everything becomes so far apart, you can't do anything. And then the universe just freezes itself out and ends. So that's really sad and depressing. The only way you get that universe is with Einstein's cosmological constant. If the universe is something else, say the dark energy is something else, we get something called the Big Rip. Now this is just cool, so that's why everyone likes it. The universe grows so fast that the fabric of the universe cannot sustain this growth, and the fabric of the universe splits apart and rips.
Wow.
I'm not talking about stars ripping apart. I'm talking about X and Y and Z, or Z in time, splitting apart. Now, luckily, if this happens, it will be instantaneous, so we don't have to worry about it. It will not happen for billions of years, so the sun will have long destroyed the Earth, and the Milky Way have long run into Andromeda, so we're all okay. But the interesting consequence of this is, if you imagine the ripping of the universe is ripping essentially all the energy of the universe. Well, if you rip all the energy in the universe, you would get some sort of big energetic event. Well, we actually had a big energetic event in our universe. What was it?
Big Bang.
Exactly. So, if the ripping of the universe happens due to dark energy, it could actually give birth to a new Big Bang and therefore a new universe. The great thing about this scenario is not only does it make us feel good about ourselves, but it could finally explain what the Big Bang was, or at least the source of it. And if the Big Bang itself was a result of a dark energy expansion ripping the universe apart, then dark energy is a carried force through this big ripping process. So we can understand what dark energy is, and therefore it actually helps us understand that dark energy is a process of something coming through the universe and fueling the universe's expansion. So, there's lots of techniques that we're trying to do. I'm trying to do that, keeps me busy. Some people don't believe, but they work. But what they're telling us is, we thought we knew a lot, but we don't, but that's okay. So what I'll do is I think I'll end there, and I'm happy to take questions.
I think I heard you say that dark energy, the force of the dark energy is not associated with the distance.
That's right.
Away from that source of dark energy.
It's the same force no matter what the distance is.
That's what I thought I heard you say.
Yes.
Okay.
It doesn't make sense, because there's just nothing else in the universe that does this.
Yeah.
The strength between electrons, nuclear force, the electromagnetic force, they all obey this rule, but except dark energy. There's a reason why people tend to don't believe this cosmological constant value, because if you get rid of that, and dark energy is a real thing, then dark energy can change with time. It can be a force that just changes with time, which is a lot more easier to understand, or at least believe. So there is some, there's some solace in that.
That even makes me believe it even less, because I can't imagine anything that could cause the same amount of force regardless of the distance. That just doesn't, I can't imagine that.
Well, and this is why we don't really understand dark energy. We just know there's something there, and we know that the universe is growing faster and faster and faster.
Right.
The reason, and I'll say this, the reason why this is believed, and the biggest evidence, is because we've observed the universe decelerating. If we only observe the universe just going at like that, accelerating, we'd have a different picture. But because we've seen the universe slow down and then speed up, we know that there has to be something going on funny with dark energy that isn't just normal. So luckily we have those measurements. So one of the things that people are trying to do, and this is where something the James Webb Telescope should be able to do well, is get this critical area where the universe went from decelerating, from slowing down to speeding up, and measure really precisely what's going on there, and then we can start to understand too. So we need to understand better the tools and then better this period. But it is a confusing thing. I can't do anything to justify it other than say it's confusing. I really can't, sorry. Yeah.
Did Gerson Goldhaber write the program to discover those supernovae?
So there was two groups that did, so there was the Supernova Cosmology Project based out of Berkeley, which Gerson Goldhaber had a huge play in. And then there was a Heisey Supernova team based essentially out of Harvard. There's a benefit to this, is you had two competing groups, competing for time, money, and glory, and they came up with the same wrong answer. And the wrong answer being the universe was accelerating. And that's why we actually had the discovery as quickly as we did. So Gerson had a big play in it, and luckily there was two groups of doing it, because if we only had one group, it would have dragged down a while until we've had another group confirm it. Now this discovery has been confirmed by multiple different techniques now. So supernova, things called baryonic acoustic oscillations, which are actually using the sound waves from the very early part of the Big Bang. Galaxy clusters, you name it, different techniques have shown the exact same answer. So we're confident in the answer, we're semi-confident in some of the tools, but we're zero confidence in the explanation. Yes?
Is there an article in Sky and Telescope that explains this parallax technique using the Willows?
No.
I mean, you'd think Sky and Telescope would write that up.
Really?
Yeah, well, it's a fairly new technique. Maybe they did or not. We have one paper that just came out on it, and we have a lot of others that come around with it. But it's a technique that's now worked on not only measuring parallax of these types of stars, but doing other measurements.
What's the name of the technique? If you want to look it up, Google it. What's the name to look under?
Fine guidance sensor dragging Hubble Space Telescope. That might come up with something. If you want to, you can go to the Space Telescope Science Institute, where they have all the Hubble Space Telescope proposals, and you can read the proposal, which provides a little bit more background about the technique. But essentially, you can use the shakes and the diameter of the Earth alone as your baseline.
And approximately when was this technique developed?
15 months ago?
Okay, relatively recent.
Yeah.
Okay.
Yeah. Yes.
So I guess I'm approaching this at two levels. Just on a very kind of low level, there's a lot of measurement error in this stuff.
Yep.
And every source of uncertainty multiplies.
Yeah.
So there's a lot of unanswered questions.
That's right. I mean, a lot of those, to be fair, just have such a small effect that it's nearly negligible, but you're right, yes.
And on a bigger level, the discovery of the accelerating expansion of the universe is a very recent and mind-boggling discovery. And I guess I just want your speculative sense of how long it's going to take for us to confidently understand what that means for cosmology. Are we talking years, decades, centuries?
With the programs I talked about here and what we're doing, hopefully mid-next year.
Wow.
I mean, essentially everything's going to plan. Our first papers are coming out in a couple months. We'll have a series of papers on a variety of the techniques talking about essentially coming out nearly every month.
So you're going to have 99% confidence of which of those curves is correct?
And hopefully a year, yeah, no later than a year and a half.
Well, that's very exciting.
So, and I'm sure I'll be wrong, but you know. Yeah.
Okay, and then in the hypothesis of the big rip.
The better one.
Yes. Okay, so is there a theory about the fate of the matter and energy in?
So that is a great question. So has anyone heard of the bicep to gravity wave inflation results?
It's in question now, isn't it?
It is. Yes and no. It's in question because part of their analysis was heavily relying on a picture of a PDF at a talk. It's since been fixed, and actually they get the same answer, luckily. But it still needs to be confirmed. But that result directly ties into this. So, this result is, if you guys don't know, 3 months ago now, a group thought they found gravity waves, ripples from gravity due to the expansion of the universe right after the Big Bang. It's a really cool thing. No one's ever found it. People have been looking for it for years. But what it does is it confirms this period called inflation. So 10 to the minus 32 seconds after the Big Bang, so really young right after the Big Bang, the universe grew dramatically in size. We're talking about 10 to the 50, so tons and tons and tons. It just went all of a sudden. It only lasted for, again, less than a fraction of a second. Now, the reason this was done was again, when you think something's not going to be right, it might be right. It was done as a fudge factor to get the Big Bang Theory to work. And everyone believed something like that had to happen, but no one actually believed it because it was just too crazy. Crazy, wrong ideas are right. And what this experiment showed was that if these ripples that they detected are true, inflation must have occurred. That the universe must have grown this rapid size in this rapidly short amount of time. Now, what does this actually mean with this? When we calculate dark energy, you can actually calculate its effects from particle physics. So if we look at the very small scale of things, subatomic particles, you can actually figure out how much dark energy has an effect on the universe. And the answer between the particle physicists, so people working at CERN in the Large Hadron Collider, and what we're doing, differ by 10 to the 120. So that's pretty bad even for us. You know, but we admit that's wrong. And the problem is, where is this 10 to the 120? Of course, it's a particle physicist's fault, I say. But what it turns out is if inflation happened in the way this experiment is detected, inflation could actually be the result of dark energy entering our universe from a larger substance. So imagine we have billions of galaxies in our universe. Well, what this thing very well could mean is there is a larger framework, something we call a brane, a B-R-A-N-E, not this brain. And there's billions of universes, each with billions of galaxies, each with billions of stars, and a much larger scale. And this larger scale could contain this 10 to the 120 in dark energy, and only a little bit went to our universe to create a Big Bang that kicked in during inflation that grew our universe, which may end with a big rip, which goes out, creating another Big Bang.
Yeah, I'm on overload.
What it really means, the base of it is, if this result happens, dark energy could be the result of a Big Bang coming through, and this inflationary period is the fuel. Imagine a balloon blowing up. It's the initial puff of air into the balloon to get it to blow up. So, we could just have billions of universes out there, just like we have billions of galaxies in here. None of which we have.
Could you tell the
I wanna
audience
ask
what
you a
your
question.
wife does?
Sorry.
Let's wait till he goes.
Well, wait, this is an important question. You're not using you're violating conservation of energy right
I violate
and left.
everything.
What?
I violate everything.
Yeah, but if you violate conservation of energy and things like that, what do you use as a guide for your physics? When I do physics, I use conservation of energy all the time as a guide. But if I couldn't use it, I wouldn't know what to do. I wouldn't know which way to go. I'd be in the black. How do you know how to make a theory if you aren't guided by the basic principles of physics as we know it?
You don't know what physics is.
What?
We don't know what physics is. What's physics?
Well,
what's time?
you're
What's
acting
time?
like
What's
a
time?
kid.
What's time?
You know, you're acting like somebody, like some hippie that smokes dope.
Hey, if I did to explain this a lot more. Okay, follow me here for a second. What did the Big Bang create?
I don't know that it created anything. Maybe it just threw stuff out. That
What
was
did it
already
throw
there.
out?
What?
What did it throw out?
I guess the stars and galaxies and mass.
The universe.
It threw out space and time.
Where did the mass come from?
And the inherent energy that it was thrown out. So it threw out space, time, and energy, right? Okay. Right?
Maybe it's condensed ether for all I know.
Fine, it threw out condensed ether.
What?
It could throw out condensed ether. It threw out whatever you want to call it. Okay?
Yeah.
Right? Before then, how do you figure out where it came from?
That's the paradox of the Big Bang.
No, that's the paradox of not you understanding physics. We don't have the tools to explain what happened before the Big Bang because the tools we use were only created at the Big Bang. So, if you have a screwdriver and you try and tighten a screw, but you try and tighten it yesterday and you didn't have the screwdriver yesterday, you can't tighten that screw. We can't figure out what happened before the Big Bang because our tools that we use, physics, math, space, time, only existed in the form we knew at the Big Bang. We can't use time to explain what was before the Big Bang because time was only in that reference frame. So, right now, I might be violating the law of conservation of energy and whatever you want to throw at it, but that's because our law is incomplete. That's because physics is incomplete. If physics were complete and we can understand what the Big Bang was, then you'd have an argument. But we don't. So we can't even begin to describe what we're doing wrong because our tools weren't there. And that's actually a great problem to have. That's where string theory and M theory tries to come into play. They try and fill this gap of what could be going on. Just as Einstein's big step was the creation of general relativity, Newton couldn't understand what galaxies were doing, and Newton was smart. Einstein had to come along and take that next step. He had to apply and say, okay, well, Newtonian physics, or normal physics, works on small scales, but we need a souped-up version, a bigger version, to explain large scale.
Let me ask you a question. I've looked at a lot of physics and cosmology, and if you open up, you can't read the paper, you can't understand it, but you can see there's a lot of X's and T's, space and time. You don't know what the equations mean, but you can see it's all X and T's and M's for mass. If you have one of these papers that tries to explain where the X and T and M come from, what are the letters that you use? What are the equations? What's in them? Are they Arabic letters? What are they?
We can talk about this after.
Randall's going to throw us out if we don't leave an expedition. But do tell the audience what your wife does. I think that's very interesting.
So my wife does something called space medicine. So she didn't have enough doing a PhD in astronomy, so she did her medical degree. So she splits her time. So I split my time between Canberra and Australia and Berkeley. She splits her time between Canberra and Australia and Houston. So she's working with the flight surgeons now, and so they've just developed the first program to do long-term space effects of human space travel. So if you look at the NASA budget, she gets much more of the NASA budget than I do.
We are so happy you
Great.
were here tonight.
Yes.